everyone. So we're looking at class number 21. Our goal is to discover Newton's 3 laws of motion. So the first thing we're going to do is head over to this PhET simulation. And when you head over there, make sure you click on the acceleration one. That's very important. You're going to turn the friction down to 0, or to none rather, so you get this icy surface. Make sure all these boxes are checked. All right. So the first thing it says to do is push the box until it reaches 40 meters per second. Don't stop it yet. So let's go to that. So I'm just going to push it, I can either click on the guy or I can click on the applied force thing. All right, so there it is, 40 meters per second. Does the velocity of the box, or what is the velocity of the box, and is it changing? So you'll notice that it's still going 40 meters per second, and it's going to keep going 40 meters per second forever. So no, it's not. What was the acceleration of the box? You can get that right from the simulation, and you can get the sum of the forces. So the acceleration of the box is 0 right here, and the sum of the forces is also 0. Okay. If you did it correctly, your box should still be moving. How can you bring the box to a stop without resetting the app or picking up the box? So let's get it to stop moving. So first way a lot of people did was they said, well, let's turn on friction. Notice what friction is doing. It's applying a force in the opposite direction. But eventually this will come to a stop. So that's the first thing you do, apply friction. So let's turn it down again, and let's get this bad boy going. All right, the other way we can stop it is by applying a force the other way. So you can click on the applied force, and you can just start applying force the other way. Notice how it's slowing down. Now, a lot of people scored a good point. They said it's hard to get it to stop perfectly. But even though it is hard to get it to stop perfectly, you can definitely get it to stop, which I hope you noticed. See if I can get it perfect. No, I couldn't get it, but pretty close. So two things you could do is you can add friction. So that's method number one, which is effectively applying a force in the other direction. Or two, apply a force the other way. All right. When the box is stopped, how can you start moving it again? So let's see, it's stopped. How can I start moving it? Apply a force, and it'll move again. So you can just apply a force. Now, every class did number 10 differently. So this might not say exactly what your class has said, but it should say something along these lines. And this is a really simple way someone put it. A force is required to start or stop an object. That's a pretty good way to put it. And I think in very simple terms, that's pretty sufficient for our purposes. We'll elaborate on it later, but for now, that's just fine. All right, now the next part, what you have to do is you have to move the friction to the middle setting. So to move the friction to the middle setting, if you hit the reset button, it'll put it right to the middle setting for you. Check all these boxes off again. And it says to apply different forces. I think the first force it tells you to apply is 150. So if I apply 150, it starts moving. I can pause it so it doesn't get away from me. I have my sum of the forces. So my frictional force is 94. My sum of the forces is 56. And my acceleration is 1.12. When I apply 200, friction is still 94. I'll see. We'll hit play so it moves. Okay. Friction is still 94. Sum of the forces is 106. Acceleration is 2.12, and then I could do it for 250 and 300 as well. All right, and you could pause it each time to help yourself read it. And when you fill it in, you should get something like this. So it says create an equation relating net force, mass, and acceleration. What you should have noticed, and it's not easy to notice with these numbers, but you should have noticed that the net force, F net, equals mass times acceleration. This is Newton's second law, actually. Okay, well, here's an example of it. 56 newtons equals 50 kilograms times 1.12 meters per second squared. Okay, and that's, if you put in your calculator, that works out. It works out for all of these. Now think about your units. What makes up a newton? Well, look here up, right over here. A newton is equal to a kilogram times a meter per second squared. So a newton is a kilogram times a meter per second squared. All right, looking at this equation here, Newton, kilogram, meter per second squared. Now, that's not the way it's written on the reference table. The way the reference table writes it, the equation anyway, is A, acceleration, equals F net over m. So putting it into a statement, force equals mass times acceleration. So if the net force acting on an object is 0, what is the acceleration of the object? Use the equation. If the net force acting on an object is 0, what is the acceleration of the object? So real quick, A equals F net over M. If the net force is 0, so A equals 0 over M, no matter what M is, no matter what the mass is, A has to be equal to 0. So if the acceleration of an object is 0 meters per second squared, does this mean that the object is stationary? Does this mean that the object is stationary? Well, we have to think to ourselves, an acceleration of 0, what does that mean? Okay. So an acceleration of 0 basically means that the velocity is constant. Okay. Now that constant velocity can be 0 or any non-zero number. Because if I have constant velocity, my velocity can constantly be 0 meters per second. That's okay. It could also be constantly 10 meters per second. It could constantly be -4 meters per second. So does this always mean the object is stationary? No. It could have constant velocity. That's positive or negative or has a value. That's non-zero. Now to explore Newton's third law, we are looking at this simulation here. Make sure you click on the model one and set it up exactly as I have mine. So let's put this away. We're going to look here, click on model, and I think the only thing that's set up is the force of gravity. All right. Now if I click on the simulation, you'll see how things move around. Now that arrow represents the force of gravity, both the force of gravity on the Earth and the Sun. Check this out. If I move the Earth closer, the force of gravity on both objects gets bigger. If I move the Earth farther, the force of gravity on both objects gets farther away. Okay, no matter where I put it, those forces are always equal in magnitude and opposite in direction. So let's jot that down. What do you notice about the magnitude and direction of the force vectors on the Earth and the Sun? Equal magnitude, which you could also say like equal strength. And opposite direction. It says play with the mass of the Earth and the Sun. Does your statement for 19 hold true? Let's do that. You already said it, so yes, let's see. If I play with the mass of the Earth, yeah, look at that. Same deal. The Sun, yeah, equal and opposite. So that holds pretty true. And what some people said was for every force has an equal and opposite force. Not a bad way to put it. So these are formally Newton's 3 laws the way I want you to know them. Okay, so pause the video here, and you don't have to memorize them, but I would be very familiar with them. The most important thing about the first law that everyone forgets is it says an object at rest will stay at rest, and an object in motion will stay at a constant velocity in a straight line unless acted upon by an outside force. Because remember, constant velocity. Velocity has both magnitude and direction. So in order for velocity to be constant, the magnitude of the velocity and the direction of the velocity must remain constant. Okay, so the in a straight line part is implied by constant velocity. The second law is pretty straightforward. A equals F net over M. And the third law, people always forget. They always say like, oh, equal and opposite forces. But just keep in mind, all forces come in pairs. Those pairs are equal in magnitude, opposite in direction, and act on different objects. For example, an action-reaction pair is like if I push my hand down on a desk, if I push on the desk with 100 newtons, the desk pushes back on me with 100 newtons. Notice how the forces are acting on two different objects, the desk and me. Okay, so just keep that in mind as well. All right, and that is class 21 for you. Have a great day.